Okay. Hello everyone. Today we are diving into Unit 5, the data link layer of the OSI model. Now, don't worry. This may sound technical, but I promise to make it super simple. Think of it like this. When you send a message online, your words need a reliable courier to deliver them safely without losing a single letter. That courier is data link layer, the one that ensures your data travels smoothly, securely, and in order. Now, let's move on. What is a data link layer? So the data link layer is the second layer in the OSI model, right between network layer and physical layer. Here's the idea. When you send something like a WhatsApp message, the upper layer decides what to send. But before that message travels through cables or Wi-Fi signals, it must be packaged and prepared. The data link layer does exactly that. It takes packets from the network layer, wraps them into frames, and sends them over hardware. At the receiver end, it unwraps the frame and gives them back to the upper layers, ensuring your message arrives correctly. As you can see here, it goes like this. Next is the sublayers of the data link layer. There are two main important sublayers. It's like two departments working together. The two are logical link control and media access control. Logical link control is like a quality inspector. It checks for transmission errors and controls the flow so that data moves smoothly, not too fast, not too slow. Second is the media access control. This one acts like a traffic police officer. When multiple devices share the same road, like cars merging into a busy highway, MAC ensures everyone gets a turn, avoiding crashes. Let's delve into the functions of the data link layer. There are 6 functions of the data link layer, starting with framing. Framing is like putting a document into a file folder before sending it. The data link layer places packets into frames, each with a label and a boundary so that the receiver knows where one frame ends and the other one begins. The second one is addressing. Again, understanding it with a real life example. Every house has a different number, address, vehicle has a different number plate, and similarly, every device has a MAC address, unique of its own. It ensures, addressing ensures that data does go into the exact device it is meant for and not the wrong one within the same network. The data link layer also follows synchronization. Just like dancers, synchronization between devices is essential to ensure that data frames are transmitted correctly. Both machines must be aligned in time to manage the flow of data, preventing loss or corruption during transfer. Error control. Moving on to error control is when data bit gets corrupted during transfer. You can see it here from an actual data example. The actual data is this, and the checksum calculated. Checksum is one of the error correction methods. So a checksum calculated is this. Here, no error is detected. But even if the first data, even if the one bit in a data gets corrupted or flipped, then the entire data at the receiver's end gets recalculated for a checksum and error is detected. Now you can see that even if one bit gets corrupted, this layer spots it and requests the correction, just like rechecking a printed document before the final submission. The next is the flow control. Think of it like a person talking at a different pace than the person writing it. The writer would not be able to capture the exact information in detail that this person is speaking because of the different paces, right? So the flow control makes sure that the data is sent at a rate the receiver can handle. Multi-access control. When many devices share one medium, for example, two people talking in a walkie-talkie, this layer ensures fair access. For example, if two people press the button at the same time, it would lead to a collision, similar to data collisions going at the same time. So this layer ensures that there is a multi-access control. Going on, you can see them in detail. Framing data layer, it plays a vital role in preparing the data for transmission. The next one is error control mechanisms. So error control mechanisms are needed because they are essential for a reliable communication. They can detect and rectify errors, and they add redundant bits for integrity checking. These redundant bits are for the receivers to verify that the data sent is matching the transmitted data, allowing error detection and correction. And common error detection methods include parity check, checksum, cyclic redundancy check, and two-dimensional parity check. Going in detail of the types of errors and their detection methods. So the types of errors are single bit error when one bit gets transmit or flipped during transmission, where multiple bits get flipped during transmission, and when a sequence or a series of consecutive bits get flipped mistakenly during transmission. Now, these types of errors create incorrect values, recovery and making recovery more challenging and potentially leading data integrity issues. So, what happens when errors are detected and how they are corrected? Let's see about that. So, the first one is simple parity check. As you can see, for the simple parity check, we add one extra bit to make the number of ones even or odd. This is quick and simple, but may miss some or more errors. The second one is a two-dimensional parity check. So the two-dimensional parity check is that utilizes parity bits calculated for each row and column of the data matrix, and allowing detection and correction for each single bit errors and some 2 or 3 bit errors. Now the only disadvantage is that although it detects 2 or 3 bit errors, it is not able to correct them. Diagrammatically, you can see two-dimensional parity check here. Rows and columns both are looked into. The third one is the checksum. Checksum involves dividing data into segments and calculating their sum. If the calculated sum on the sender side is the same as the receiver side, then the data has not gotten corrupted. But if it does not match, then the data is definitely corrupted, as you can see in the picture. The last one is cyclic redundancy check. This one is a pro level checker. It divides the message using a special binary pattern. If the remainder is 0, it's perfect. But if not, the data is corrupted. This is used in major services like Ethernet, Wi-Fi, and even USB drivers. Two-dimensional parity check, checksum, cyclic check. Now moving on to multi-access in data link layer. But wait up, did you think that if an error is detected, what then? So here ARQ comes. That's where ARQ steps in. It automatically asks the sender to retransmit the frame, and it's like politely saying, hey, can you repeat that? I didn't catch it correctly. Now finally moving on to multi-access in data link layer. So the data link layer has several is when several devices share a single communication line. We did that, didn't we? So the first one is the Aloha. It was designed for wireless LAN but is now also applicable for a shared medium. It is one of the earliest methods and has two types, pure Aloha and slotted Aloha. The pure Aloha is when two devices send data whenever they want. It's like people freely speaking on a walkie-talkie. So if two speak at once, both messages collide and are resent. The second one is the slotted one. It is better and is improved by giving time periods where the messages should be sent so that everyone speaks only in their turn. The last two are CSMA-CD and CSMA-CA. Now, CD is collision detection and CA is collision avoidance. Collision, if a collision happens in case of both devices sending together, both devices stop and try again later. This is used in Ethernet. Now, in order to avoid collision entirely, there is CSMA-CA. This prevents collisions altogether and is often used in Wi-Fi. It's like saying, excuse me, I'll go next, creating a sequence. The last one is DOCSIS. It's a real world example. To see this in action, let's talk about DOCSIS, Data over Cable Service Interface Specification. It's what allows your broadband internet to run over TV cables. The MAC sublayer manages how multiple households share the same cable effectively. From DOCSIS 1 to DOCSIS 4, there have been multiple evolution and it gets updated every time. From DOCSIS 1 just given 40 Mbps to DOCSIS 4 offering multi-gigabyte speeds, it is the data link layer that makes sure your Netflix stream never freezes. So summing it up, you can see this? Yep. Now, to sum everything up, the data link layer is the guardian of smooth communication. It breaks data into frames, gives each a unique address, checks for errors using CRC and parity, resends lost frames with ARQ, and ensures everyone shares the channel fairly. It is an unsung hero that keeps the internet running without chaos. Just a question for you before it ends. Have you ever noticed a Wi-Fi drop and wondered how CRC or ARQ help fix automatically? I would definitely love to know, and this video would help you answering it. Thanks for watching. I hope the data link layer is more clear and less of a mystery now.